Hello everyone. Welcome to our second invited talk of CHES 2024. Before starting, I would like to say that we are deeply grateful to our two invited speakers, Professor Bart Prenell yesterday and Dr. Sam Jaques today, for accepting our invitation to deliver these invited talks in CHES 2024. So before starting, I will say some words about Sam. Sam Jaques is an assistant professor at the University of Waterloo. He completed a PhD in the University of Oxford, and his research focuses on quantum resources estimations and how hard will quantum attacks be in practice. He has analyzed quantum attacks on symmetric crypto, post-quantum crypto, and elliptic curves. And in 2019, one paper co-authored by Sam got the Best Paper Award in Crypto 2019. So with that, I would let you with Sam. He will be talking about quantum attacks on AES. Please, Sam, the floor is yours.
Hi, everyone. I'm really honored to be here, really honored to have the invitation to speak, and also getting a bit of kind of imposter syndrome because I'm not a cryptographic hardware or embedded systems person. Really, the only way I could be is if we consider a quantum computer as cryptographic hardware. And that's kind of what I think about a lot. And so I was sort of asked to talk about quantum computing and thought it made sense to focus on this very particular question about quantum computers. So when do we need to worry about structureless, quantum, known plaintext attacks on AES in particular? So more or less, do we need to all move to AES 256? So covering some very basic background that sort of everyone I'm expecting to know, but I want to think about just known plaintext attacks. So you have your plaintext, it's encrypted, you want to recover the key from this. So many interesting talks in this conference about all kinds of different threat models. I want to ignore all of that and focus on this just very basic textbook one. Kind of every adversary should be capable of mounting this attack. And I'll focus on AES, but you could think about other block ciphers. And you could also sort of think about what I'm about to say for hash pre-images. And I also want to think about just structureless attacks. So I want to assume that AES is well designed and we don't figure out some structural weakness that breaks it in a weekend on a laptop. That really our best method is kind of trying keys. So forget about differential cryptanalysis, even interesting quantum structured attacks like period finding. And here's just a biased set of references if you're interested in kind of quantum structured symmetric cryptanalysis. But I'm kind of forgetting all of that. I just want the structureless attack. So what do we do classically if we don't have any structure? All we can do really is kind of a guess and check, right? So we go through all of our keys, we encrypt the messages, we check if it matches the ciphertext, and if it does, we say great. Maybe we need a couple for false positives, but more or less this works. So the runtime is proportional to the size of the key space, and this is exponential in the length of the key, so it's exponential growth and therefore secure. More or less. Well, so what about a quantum computer? So the quantum computer has an analog of a brute force search due to Grover. And Grover's algorithm is actually very similar to the brute force search. So it repeats two steps. The first one that I said is this diffusion operator. It's like the quantum version of picking a random key. And I say it's cheap quantum magic to say, don't worry about what's happening internally. It's something that in almost any quantum architecture you'd envision, this will be an easy step to do for the quantum computer. The hard one is the checking part of guess and check, is that it actually has to compute the block cipher, like AES, and it needs to do it in superposition and then check the result. And this second step means you more or less would need to design a quantum circuit to do AES encryption. And that actually ends up being the focus of a kind of a niche field of research. Kind of creates a lot of the cost of the attack. But the quantum advantage here is that the top bound of the for loop is the square root of 2 to the n. So it actually runs in square root of 2 to the n or 2 to the n over 2. So it's this square root speed up, at least asymptotically. So this is kind of why people think, oh, maybe we should double key sizes. But is this actually a threat, right? So I mean, classically, it's exponential time to break a key, but we actually need to figure out at what size does this become infeasible. So we kind of all know if it's 56 bits, it's DES. This is too easy. If it's 64 bits, I don't think I could afford to break that, but like the NSA could. 128 bits or more, classically, we're kind of mostly in agreement that this is safe, right? All of these numbers are numbers that kind of we learn from practice. You learn the hard way with DES, and we go out and we look at devices and we say, how powerful are they? Like if you actually spent a lot of money, how much compute could you buy? That's hard to do with quantum computers because they don't really exist. So I mean, from a quantum attack, a 1-bit key is safe today because you can't do like you couldn't do one encryption with it, right? So you couldn't check one key with a quantum computer today. So okay, n equals 1 is safe. But we expect quantum computers to get better. So maybe n equals 64. We take the square root speed up. It's about equivalent to a 32-bit key. This is about the same complexity as breaking RSA. So if we expect quantum computers to be a threat at all, which I do in the long term, then obviously this key size would be vulnerable to a quantum attack. Also not that interesting because it's already vulnerable to a classical attack. So then we look at the interesting case where we have n equals 128. So the attack should be on the order of about 2 to the 64, which classically is doable, but when would a quantum computer be able to do that? And is it really this, or are there constants, right? I keep using this big O, but I haven't told you what the constants are in here. So let's try to figure out the constants. So this has been, again, I say a little bit of a field of research. So most of this comes down to Grover's algorithm, the number of iterations, the constant is kind of on the order of almost 1. I think it's around 1.5. The hard part is the quantum circuit. And so people have tried to design these quantum circuits, and there's been lots of follow-up work, but I'll go kind of to the first one that I know of from 2015. And so they tried to design for the key sizes, 128, 192. They have a number of gates and depth and the number of qubits. Okay, so you can kind of see an increase in the number of gates over 2 to the 64. But you might also say only 3,000 qubits. And maybe you're keeping up a little bit with quantum computing news. And you have all these articles that are saying we're going to get this 10,000 qubit machine in 2 years. IBM saying they've made room to expand to thousands of qubits. Another article, IBM is imagining over 100,000 qubits. They've got these visions. So maybe you think 3,000 qubits, that's probably not too far away. Maybe we'll have that next year. Wouldn't surprise me. Okay, well, so we can get the qubits pretty soon. What about the number of gates? Is this a lot? And then you think on kind of the scale of computation. Well, the Bitcoin network does about 2 to the 69 hashes per second. So the number of, if we equivocate a hash with the quantum gate, then 2 to the 86 gates is about 36 hours on the Bitcoin network. And so reasonably, you could conclude from all this, if you're not a quantum computing expert, you could put all this together and say the scale of Grover's algorithm on AES-128 is roughly at the scale of next year's quantum computers and the Bitcoin network, right? So maybe this kind of makes it seem within the realm of possibility. So I mean, if you make this conclusion, I would say you're completely incorrect. It was a reasonable thing to guess. And so what I want to say in this talk is my own opinion and how I get here. I don't actually think Grover will break AES-128 in our lifetimes, and probably never will. In the same sense that kind of the scale of a classical attack, I'm also skeptical that we'd actually ever do 2 to the 128 encryptions. So that's kind of what I want to step through. And along the way, this will nicely, I'll cover some things about quantum computing and sort of how I think you should think about quantum computing. So misconception number 1 is that qubits are the limiting factor for quantum circuits. And this has sort of been true. Companies and academics have struggled to build machines with more qubits, but the situation's a little more subtle. So I'll kind of give a crash course on quantum computers. First thing, what is a qubit? I've been using the word a lot. It's really just analogous to a classical bit. So it's some sort of device that holds quantum data. Quantum data can be 0 or 1, but we write these funny brackets around it to indicate that kind of we can do more than this. We can have these superpositions where we make linear combinations of 0 and 1. And when you have multiple qubits, you can have more quantum data, kind of many of these zeros and ones, and you get the interesting phenomenon like entanglement and interference. But it's kind of the fundamental unit of data. If you want to do a quantum computation, you need to hold the data, you need qubits. What are these? So anything that is a 2-level quantum system. You can have superconducting qubits. This is what IBM and Google use. You can have a little superconducting wire, and one way to hold the qubit is which direction of current. You can have trapped ions. So you sort of hold them in this machine, and you can have kind of whether they're in a high or low energy orbital, and this is your 2 states. You can have photonics, where you'd have maybe 2 fiber optic cables. Photon on the left is a 0, photon on the right is a 1. Once you have quantum data, then you need to actually compute on it. So you would have gates. And think of these kind of like classical gates, but a key distinction is that a classical gate, mostly that's a physical thing you can point to. I mean, you can actually look at the chip, and if you had the big enough microscope, you could say this point here, these transistors are this particular gate. And that's not what a quantum computer, it doesn't seem like that's what quantum computers will be like. Instead, a gate is some sort of process. So for the superconducting qubits, you shine a microwave laser pulse at it. And so that is the gate, like that changes the quantum state. And so you can't point to anything and say, this is the gate. The gate was something that happened. And so if you see something like this thing takes 2 billion gates, it's not that you need to build 2 billion devices into your machines. You need to do something to it, almost like 2 billion clock cycles or something like this. So we can hold we can hold data, we can compute on the data. The other big thing for quantum computers is noise. So kind of just anything that you didn't want to happen to your quantum state, but happened anyway. And this ends up being a lot more difficult than classical noise. And so I'm going to be going out of my depth speaking to this audience about classical noise, but mostly, if I had some chip and a little bit of energy gets in it, it's not going to really break the computation, right? You have to work a little harder. Whereas with a quantum computer, even a little bit of interaction is a little bit of error, and it can accumulate over time. So you really need kind of no unwanted interaction, that's why they build these big bridges. The other thing about quantum computers is a qubit can have a bit flip error, where a 0 becomes a 1, or a 1 can become a 0. But they also have phase flip errors. So 1 becomes a negative 1. And you probably don't have any intuition for what this means. It takes a while to make one. But you can also have any linear combination of the two. So you have an infinite number of possible errors that your quantum computer could have. And this really makes them fundamentally more difficult to manage. And there's kind of some results that things that work classically don't work quantumly to take care of the noise. So given all of this, when I think about quantum computers, there's lots of dimensions that we can think about. The 2 most important to me, if we have to compress it, would be the error rate and the number of qubits. And even making the error rate into a single number is kind of compressing the data more than it kind of can be. So when you look at this chart, I mean, I'm not trying to endorse one company or the other, sort of giving a broad overview. Here's roughly where we are, right? About 100 qubits, error rates of about 1 in 100. And okay, where do we need to be to start attacking crypto? So if we want Shor's algorithm, it is about 1 billion gates. We need the error rates about 1 in 1 billion. And that shoots it way up there, about 7 orders of magnitude lower errors than we are today. That seems like a pretty big engineering task. But this talk is actually about AES, not even RSA. So Grover, we have to shrink the axis like this. We're several, almost more than 20 orders of magnitude away in terms of error. This feels kind of insurmountable, and I think it is. So what do we possibly do? Well, we use error correcting codes. So we're not going to make the little superconductor have 10 to the minus 25 error rates. There's a whole field of quantum error correcting codes, just like classical error correcting codes. You take your quantum data, you add some redundancy, you encode it in many qubits, and they will act together as though they were one much better qubit. And so there's some important lingo. This is one of my big takeaways from the talk that will help you contextualize quantum computing news and results. So people talk about physical qubits. That's like today's devices. So if you read these articles that say IBM's going to have 1,000, they mean physical qubits, the actual superconductors themselves. A logical qubit is the abstraction representing what you get when you combine them together with error correction. So if you see a paper, and there have been a few published in CHES, that kind of design quantum circuits for different things, pretty much all the time, these are thinking about logical qubits. And the ratio is about 1,000 to 1, kind of our best methods. And why do we think about error correcting codes? Why do I think that this is a key piece to understand quantum computers? Basically, imagining that quantity is easier than quality. So we could try to make one qubit that's 1 billion times better than they are today. I think that would be much harder than making them 10 times better and then just building 1,000 of them. Because once we have 1,000, we can use the error correction to make it effectively 1 billion times better. And I'll actually talk a little bit about how the error correction works. So the big thing that people think about is called the surface code. And it's the most practical, and the reason is, well, so what it looks like is this grid, this two-dimensional grid. The black and white dots are the physical qubits. The yellow and the green represent the interactions between them. So each qubit only interacts with the qubits that are right next to it. So this is a plausible architecture to build. You can kind of imagine printing out a chip and actually aiming the lasers in a way where this whole thing could make sense. And so your logical qubit here would be one of these kind of patches. So maybe this would be one. Usually they'd be square to kind of match the two different kinds of error. And the error suppression is exponential in the width of this grid. So if you don't have if your error rate is still too high, you add one more row and one more column, more or less, and you get kind of a multiplicative improvement. Takes a lot of work once you have a surface code to even maintain the quantum data. It's not like you just sort of encode it and then it stays high fidelity. You have to constantly be doing these measurements, a bunch of co-processing to keep your data. But it could work, right? It's going to be expensive, but probably worth it for something like factoring. The extremely exciting news in quantum error correction came actually last week. And this is one of the biggest results in quantum computing I've seen. They basically made a logical qubit in the surface code, more or less for the first time. So the big breakthroughs they have, the different colored lines are the different distances. So they're making the grid wider. And you can kind of see the lines are getting more shallow. The error rate is going down the bigger they make the code. Sort of the thing that has to happen for this project to work. And the dashed lines are their physical qubits. And the bottom one, the blue one, is their logical qubit. So their logical qubit now, it's better than the physical qubits. And they ironed out a bunch of extra kinks. They have their decoder that can actually keep up with all the measurements they need to kind of correct and detect the errors. So this is kind of huge. But it's 105 physical qubits. Where does that put us compared to where we need to be? Sort of as a quick aside, where does RSA break? So, there's Google kind of on the frontier of quantum computing today. This blue region is roughly where surface codes work. And way over on the right is how big they need to be to break RSA. So we're pretty much where we need to be in terms of error rates, but we need 20 million qubits compared to the 100 we have today. So I mean, I expect this to happen. I hope and I expect that by the time I retire, quantum computers will break RSA. So back to the main subject of the talk, AES. What about Grover's algorithm? So if I throw this on here, it's a black line pretty much right in the middle of RSA. So actually the physical qubit requirements to run this are not too much worse than RSA, which seems kind of weird since it should be much harder to break. But this chart has ignored runtime entirely. And so in fact, AES is going to take a massive amount of time with just these qubits. But it's also it's not 3,000 qubits, it's on the order of maybe 20 million. So my summary of error correction, again, the big takeaway I'll repeat, the physical qubits, that's what we see today. And the logical qubits are the things that we need to make real circuits, the translation is about 1,000 to 1. Every logical qubit will need about 1,000 physical qubits with the surface code. It's expensive to maintain them. And also something that will come up is that the gates that you can perform on them kind of change. With an error-correcting code, you're working so hard to kind of keep the quantum data from being modified, but then a gate is modifying the quantum data, so you have to kind of undo what you did with all the error correction. So correcting this misconception, even if the physical qubits are limiting, which they still sort of are, the translation from the logical qubits that we need to run these cryptographic attacks into the physical qubits is non-trivial. It's going to depend on error rates and on layout and all kinds of things. So the second one, kind of the big one, because of this square root speedup, we should double our key sizes, right? Well, what would a Grover attack actually look like? Imagine you're put in charge of the organization. You start hiring the engineers, ordering the machinery to do this. To take a step back, let's imagine attacking a DES, and it's probably not imagination for a lot of people here. So I tried to find a number on how many clock cycles on a modern CPU is one DES encryption. And so I'm probably embarrassing myself by guessing at 100 because I couldn't find a nice number. But put the right number in here. It won't affect the conclusion too much. Take a very fast CPU, and we know the DES is broken. We've had kind of 40 years of advance since the 80s, so it ought to break it quite quickly. But actually, if you put the numbers in, it should take 46 years, which kind of seems surprising since it doesn't take 46 years to break DES. And the reason is because you're not just taking a single-threaded CPU and telling it break this and going for coffee. All realistic attacks are parallel, right? You would absolutely buy more compute, you buy more processors, and you throw them at this problem. And for that reason, when we're thinking about attacks, it makes sense to think about the fact that in basically every situation, your adversary has some sort of time limit, right? For a lot of the things that I want to keep secret, after I die, I don't really mind. If I'm a nation, there's going to be some secrets that really only have a lifespan of weeks, if it's maybe like an active military operation or maybe a much longer lifespan, but there is some time where kind of you stop caring. And so when NIST called for post-quantum cryptography, and they were trying to say, how do you analyze the quantum security? They included this, and they said you should consider the max depth. So this would be, how long does your adversary have? And they gave 3 options with different reasoning. So one of them was 2 to the 40, which they said presently envisioned quantum computing architectures. I think they meant a surface code. So basically, you have a surface code, you run it for a year, you get about 2 to the 40 logical operations in a row. 2 to the 64 is you've made your quantum computer as fast as a modern classical computer, and your adversary has a decade to break your crypto. And the last one they gave is kind of really pushing the bounds of reason here, just trying to use physical bounds here. So they're saying, all right, let's say you make your qubits 1 atom wide. Well, some of your gates are going to have to move information from one qubit to another, and information is limited by the speed of light. So light will take some amount of time to go from one atom to the one next to it. And if that's your gate speed, and your adversary also has a budget of a millennium, you still only get 2 to the 96 operations in a row. So these are kind of saying this is a sort of a hard limit. If your attack takes longer than this, it doesn't really work. And this is something that with classical attacks, generally, I think people sort of forget about, because most of the big classical attacks parallelize perfectly or almost perfectly. So if you want to trade off runtime to total operation count and number of computers, it's more or less the same. But Grover search actually does care. And you don't get this nice property that you can trade them off perfectly. And I'll step you through the mathematics of why that is. So it turns out it was proven not long after Grover published his algorithm that if you want to run it in parallel, your best method, if you have p quantum computers, is you simply take your search space and you split it into p subsets. So let's say I've got 16 quantum computers. I say to the first one, check all the keys that start with 0000. Say to the second one, check all keys that start with 0001, and so forth. Now, one of these quantum computers has gotten lucky, and the partition that it's supposed to search actually does have the secret key. So how long does it take? Well, the space it's supposed to search is 2 to the n over p, and it gets the square root speed up, so the time is the square root of 2 to the n over p. So I mean, it is faster, but our original time was the square root of 2 to the n. So the factor of reduction is only square root p. So compared to classical, if I have 100 machines and I want to do a brute force search, I get the answer 100 times faster, more or less. If I did the same thing for a quantum search, I'd only get the answer 10 times faster. And even worse, I have to, I don't know which quantum computer got the lucky partition, so I'm searching over all of them. If I'm considering the cost in terms of total operations, this has now gone up because I have this runtime of 2 to the n over p times p, over square root p. I get a factor of square root p. So the more I need to parallelize, the more the total cost of the attack, and more or less because of depth limits, because you kind of have a time limit on your secrets, you have to parallelize. And this is sort of main takeaway number 2. And this is, I have to emphasize, this is not my observation. This has been kind of folklore for years. Grover is going to parallelize very badly, and that really limits its effectiveness. I'll pause here for another kind of sub-misconception. If you're familiar with NIST's criteria, you might have thought that it was because of decoherence. So if you have a qubit today, you really only get a fraction of a second before it just decoheres. It loses its quantum state. But I really don't think NIST limit reflects that. Basically because if you have a sufficiently long decoherence time to do some computation, then you just kind of wrap that in another error correcting code and you get a much longer sort of effective time for your qubits. So thanks to quantum error correction, I don't think decoherence is really holding you back very much. But really the time scale of the value of cryptography is what's important. Yeah, secrets are not valuable forever. So putting this all together, this makes parallel Grover attacks actually so expensive that the more you parallelize, the more you're losing your relative advantage to classical computing. So it suddenly becomes not really a square root speed up, but it is much less, depending on sort of the constants involved. And this, when I work through the constants, it just doesn't seem like it's going to be feasible in our lifetimes. In the same way that I don't expect classical computers to break AES 128 with a brute force search in our lifetimes. And possibly never. I mean, when you start to look at the fundamental physical constants involved here, we're pushing at them. So then the last one I want to talk through is that it's going to take 2 to the 64 times some small constant, where the small constant is well known. And so already we've seen a problem. It's not going to be 2 to the 64 because of the parallelism. What about this constant? So now my other kind of crash course is quantum circuit design. What is a quantum circuit? Theoretically, the same as a classical circuit. It's a list of which gates you apply to which qubits and in what order. And again, recall that these are a process, so it's more like a set of instructions than it is like a blueprint for something to build. Here's just some examples of quantum circuit diagrams. The lines are qubits and the annotations are gates. So kind of the third qubit down, we apply this H gate. And then these other 2 qubit gates and so forth. And just like with classical circuits, we have to decide what gate set is natural for our architecture. And there's different universal gate sets. And the one that we often consider is Clifford plus T. So it's universal. If you have any quantum circuit, you can express it with these gates. The Clifford gates are easy to apply on a surface code, so it makes sense to include those. And T gates are not easy. They require something called magic states, sort of this resource that you get and you kind of consume every time you want to do these T gates. And so it ends up being that these are the more expensive ones. So you often emphasize those when you're designing circuits. But this is the typical choice. So let's say you want to design your circuit to attack AES. You want to find the cost of each iteration in Grover's algorithm. So quantum theory basically has this result that if you have any classical circuit, you can transform it to a quantum circuit and you have only a polynomial overhead. So you can take this, lots of good research on efficient circuits for AES, and you would just kind of plug this into this machine and you would say, here's a Here's a quantum circuit. But quantum circuits actually have to be constant time and reversible. So the overheads in this are not, they're nothing to sneeze at. So it often makes sense to actually kind of do this by hand and go through and design a quantum circuit more directly than just sort of a compiler from a classical circuit. But once you start designing by hand, then you have the question of what are you trying to optimize for, right? And there's lots of things we could pick. We could pick a number of qubits, but I sort of already argued that's maybe a red herring. There's runtime or depth, number of gates. And what often happens also is because it's hard to think about quantum computing. It's non-intuitive. So a standard practice has been, okay, you design a reversible classical circuit because quantum computing has to be reversible, more or less. So you build it out of XOR gates and AND gates, and you make sure it's reversible. You translate those to quantum gates. So there's the X, which is like NOT, and C naught, which is like XOR, Toffoli, which is like AND. And then you translate all of those to Clifford plus T. And kind of a confusing point that is an unfortunate notation of the field, the T in T gate does not stand for Toffoli. They're entirely separate gates. But confusingly enough, on this last translation step into Clifford plus T, the only gate that needs T gates is the Toffoli gate. So Toffoli implies T in this sense, but it doesn't stand for T. So if this is kind of confusing, you can mostly ignore this, but it's a bit of a pitfall of the field. So once we have this idea, how are we designing these circuits? So should we optimize for total gates? And this makes sense because they might be costly. It might take some computation to figure out when and how to do it. It might be the energy for a laser. But which ones do we count? So if we design in the with Clifford plus T gates, this makes sense for a surface code, right? I said this is the Clifford are natural in a surface code. But what if we come up with a better code? Is it going to be the same gate set? Well, what happens then? So the first thing is, we're not going to get a gate set where every gate is easy. It turns out that you can't have a universal gate set and all of them be easy to apply on an error-corrected qubit. The other thing is that you can convert any gate set to another with kind of constant overhead. And this makes sense, right? If it's universal, I have gate set A and you have gate set B, my gate set can simulate every gate in yours, so I just sort of substitute. But if we're having this constant overhead and a conversion between them, it's kind of why engage in this exercise to begin with, because we already have generic conversions from classical circuits. And the other thing we could do is optimize for Toffoli count. So this is a little more abstract, and we're saying, okay, we're not quite sure what code it's going to be, but probably in the code, the Toffoli would be the hardest. And you can sort of expect this because an X is like a NOT and a C naught is like an XOR, so you can simulate them both with Toffoli gates. So it ought to be the hardest one. And just as illustration, here's a diagram of a Toffoli in the surface code. You don't need to understand what's going on here. I put this here because it looks complicated, because it is complicated. It's a tricky thing to do. However, you maybe saw asterisks on the previous slide. There's modern quantum techniques that break from this reversible paradigm a little bit. So a quantum computer, as you know, is more powerful than just a reversible classical computer. People have started to figure out ways to use that power even for some of these very fundamental things, like doing these AND gates. So things like measurement-based uncomputation allows you to kind of do better than reversible computing. So maybe it doesn't make sense to even design a reversible circuit in the first place. And we could start optimizing for depth maybe, because we know that runtime is not included here, but it's a very important factor for AES. I had my whole section on how runtime is important because of parallelism. We could also focus on depth times width, thinking of something like the area time cost of a circuit, but maybe we're thinking about all the computations we have to do to maintain the error correction. And kind of the sum total of those is the runtime times the number of qubits. And for Grover's algorithm in particular, we could choose different metrics, because let's say that I'm thinking about the gate cost of the overall attack. Well, remember, let's say I can only fit 200,000 AES encryption iterations in my time budget, right? If I make the quantum circuit twice as fast, then I can fit twice as many iterations. But because of how badly it parallelizes, that means I've reduced my parallelism by a factor of 4. I get kind of this squared benefit for every reduction in depth. So when I'm designing the AES circuit itself that will go into Grover's algorithm as a subroutine, there's a huge bias in my cost model to optimize for depth. So we worked out the details on this. If we wanted to optimize the gate cost of the overall Grover search, then within the AES circuit, what we should optimize is gates times depth, and similar for the depth times width. And so this is something that we noticed in our 2020 paper, where we, kind of tried to improve on these quantum circuits for AES and tried to come up with a better number. This has since been improved to a result from Zhang et al. And I'll get back to this one. But there's lots of different choices, and I've kind of pointed out the issues in them. I don't really know which one is right, and I'm not sure we can know which one is right. I have a lot of doubts, actually, about this entire field. So it's something that I've worked in and now being quite critical of my own work and the other work in the area, that I think maybe it was kind of premature. So if we're thinking about the Clifford plus T gate set, it's natural for the surface codes, but an actual surface code is even more complicated. So I'll talk a little bit about this. These are fun diagrams. So remember that the surface code is a big grid of qubits, and I take little squares of them and they work together and they store one logical qubit's worth of quantum data. But remember that they only had nearest neighbor connectivity. So if I have a logical qubit over here and another logical qubit over here, how do I make them interact? Well, I actually have to move the quantum data from these physical qubits to physical qubits that are over here. And we envision a system where the physical qubits are really kind of locked in place. They're manufactured into the chip. But there's operations we can do on the code that will basically move the logical qubit around. And so when we're visualizing the surface code, we think about this stationary grid of millions of physical qubits and kind of the quantum data sort of swimming through it. And since it's a two-dimensional grid and we're thinking about moving through time, why don't we represent this in 3 dimensions? That's what this diagram is here. The bottom 2 dimensions are kind of this implicit grid of millions of physical qubits, and each little tube is one logical qubit moving through time. And you can kind of move it. You can see it kind of moving through the grid to interact with another logical qubit. They make these fun diagrams. But now all of a sudden we have a routing problem. That our quantum circuit, we need to make sure the right qubits are next to each other to interact with each other. We need to provide extra space so that they can move around. Turns out in a surface code, X gates are free. You just do them with the classical coprocessor when you do all the error correction. So you don't even need to account for them. H gates are almost free. They're very cheap. So it's this little yellow strip. You can see that on the scale of what's going on, that doesn't really matter. This is what I called cheap quantum magic in I think slide number 3. This is why it's so cheap. C0 gates are interesting. They're a Clifford gate, but to do them in the surface code, you actually need this sort of piping. So again, this creates these kind of routing problems. And even there's 2 colors on these diagrams, and you have to get the colors right, which makes these wacky sort of shapes. And then finally, your Toffoli gates require these factories, and it's just this enormous layout and this enormous amount of time. You can kind of see the little squares in here. That's one logical qubit. So each little square is thousands of physical qubits. It's just this massive portion of the layout that you need for your quantum computer to do these factories. And so all of these are complications that haven't really been accounted for in analyzing Grover search and AES. So the logical circuits designed kind of ignored these difficulties. And the circuits are based on a gate set that the best justification, at least to me, is the surface code. So this kind of creates this paradox. If surface codes continue to be the best quantum code that we come up with, then these cost estimates are incomplete. We didn't do all the routing. This stuff isn't there. But if surface codes get replaced by a better code, then we probably need to redesign the circuits in a new gate set. And so either way, our estimates aren't really complete. And going back to this, why didn't we make surface code layouts in this 2020 paper? The good reason is it would be premature to assume that surface codes will continue to be the best. And so we're trying to be a little bit more abstract and a little bit more generic. That's probably what we wrote in the intro. The real reason is there's no good tools that existed to work with surface code layout. So I've shown you all these diagrams from other papers. These were all made sort of by hand in SketchUp. So I can't confirm this, but I'm pretty sure it's just Craig Gidney from Google has drawn basically all of these. I've tried to do this, and it's a real pain. So it just makes the whole field sort of hard to do. But adapting a tool from Google, I had a summer student, Grace, and we worked together to build something that actually makes this a little more straightforward. So you just write Python code that says, I've got a qubit, I want to move it to here, I want to make a CNOT, and it kind of automatically figures out your layout, and you get diagrams like the one on the right. And I swear this will be public in very, very soon. And so this, to appear in CHES 2026, you can take this tool and you could do this. You could make these quantum surface code layouts, and you could say, this is what on this far future embedded device of a quantum computer, this is what AES is going to look like. And, as an invited speaker, I get to kind of take a step back and say, okay, you could write this paper. We have roughly the research and the tools behind it. But should you write this paper? Is it actually telling us something interesting that we didn't know about quantum attacks and AES? And as you can imagine, the punchline is, I don't think so. And to step through this, so here's this paper I said that was kind of the best in terms of the metric that I think is right, which is the overall sort of depth times width cost of a parallelized Grover search. So if you're running it in the surface code, you probably have a depth limit of about 2 to the 40 operations. And if you wanted to actually run this means you need about 2 to the 80 logical qubits to parallelize this machine. So I'll pause there for a minute to just let 2 to the 80 sink in as the scale of thing we're thinking about here. And to make the surface code, it's pretty good at suppressing errors, but this is a big algorithm, so you need a fair bit of error suppression. So when you crunch through the numbers, the translation of all of your error correction co-processing, the number of operations is about 2 to the 16 per kind of qubit time step. So if you multiply this by your depth and your number of qubits, your total quantum operations is going up to at least 2 to the 136. And this is from these circuits that weren't even considering surface code layout. Once you actually account for all the extra features that I mentioned, this is definitely going to bump up. So I mean, we've massively lost our square root advantage, right? For perspective, NIST estimate on the, I think this is the gate cost of breaking AES, is 2 to the 143. So we're a factor of 2 to the, we're only 100 times better than a classical attack using this giant quantum computer. And I mean, this is starting to get completely impossible. So there's all kinds of physical bounds that we can throw on it. Landauer's law is a classic one. Basically from thermodynamics, the second law of thermodynamics says that if you want to do one non-reversible bit operation, you need at least Boltzmann constant times temperature times longitude joules of energy. I'm sure from personal experience, you know that one bit operation is going to be a little bit more expensive than that, probably a few orders of magnitude more expensive. And okay, quantum computers are reversible, but the error correction isn't, so we can count those operations. This attack, using this very fundamental, very optimistic physical bound, is going to take 2 to the 55 joules of energy, or about a nuclear power plant running for 1 year. So now if we start adding in the overheads of the fact that this is not a realistic physical bound, we're thinking maybe thousands of nuclear power plants. It doesn't seem possible to me. If we make the qubits 2 microns wide, this is going to be moon-sized. So I don't think that's going to happen. And okay, I'm being a little unfair because we had to really parallelize this thing, and that's what's making it so expensive. So we could maybe imagine a version where we have, the 2 to the 96 depth, but recall that that's speed of light gate propagation over atomic scale qubits. This will never be built. This is not a real machine that we should be considering. So I mean, overall, we're starting to get into the realm of, well, will our adversary build a giant Dyson sphere that will run Grover's algorithm, or throw it in a black hole and have some sort of general relativity? But I mean, this is science fiction, and not in a bad way. So I mean, the talk yesterday, brain-computer interfaces are science fiction, but it's scarily real. That's something that we kind of should be concerned about. I don't think the Dyson sphere Grover algorithm is the same thing. And so when I think about this paper that you could write, and I could write, and I drawing these circuits is fun. I don't want to embarrass myself by actually doing this because it's fun to make the little layouts. So I might do this anyway. But I think the important thing is that on the surface code, this will just never succeed. Like when we work through the numbers of how big of a computation this is going to be, it's just not worth considering. And so I think this is kind of an important part of this paper, is to go through the numbers and say, oh, right, we don't have to worry about the surface code. We're not going to break AES 128 with Grover's algorithm unless we improve on the surface code. And so this is kind of my main misconception here. The overheads are huge. They're not really a small constant. I also don't think they're well known because of all the uncertainty in what the architectures are going to look like. I hope I've kind of sold you that Grover's algorithm is a very far future attack. So I mean, there's a whole paradigm of quantum computing shift from where we are today to breaking RSA. And then there's at least 1 or 2 more shifts before Grover's algorithm might be feasible. And by the time we've gone there, I don't think we can confidently predict the architecture and confidently design a good circuit. And so this is my kind of getting to the conclusions here. So going back, this is the 3rd time I'll say it, but physical and logical qubits are different things. Keep that in mind when you see quantum computing news or quantum computing research. Grover's algorithm has this bad parallelization problem. And so it's not really the square root speedup that the theory says it's supposed to be. Guessing optimal AES circuits, I think, is very hard and possibly even pointless at this time. And all of this together, I think AES is probably safe from classical and quantum attacks in our lifetimes. And so then we have the question, should you upgrade your key sizes? And I think I'm confident enough to say this last point. I'm not confident enough to say that you shouldn't use AES 256 because there's lots of other things you could consider. And I think Daniel Bernstein basically has made the same point before and concluded with, you might as well upgrade because it's not that much more expensive. So keep these things in mind, but this is I want to just focus on just the quantum attack cost. So thank you. I'm happy to take any questions.
Thank you for the nice presentation. We have time for questions. You guys have questions? Meanwhile, I have a question for you, Sam. So from what you said, I understand that IBM is advertising more qubits in their machines, but maybe with less quality. And with this result that you mentioned last week of Google, they are going for more quality in the qubits. How do you think these strategies play out? Could you comment on that?
Yeah, that is kind of the impression that I have of the field, is that, oh, and actually I threw in a bonus slide for this kind of situation. So yeah, I mean, IBM has this, they have this big device and they have lots of connections, but lots of them end up, lots of the connections between qubits end up being quite bad. And Google's been a little more slow, and they had a 72 qubit device maybe 5 years ago, and now their biggest is only 105. So it's not a fast improvement, but it's so much more capable. So the risk of being I try not to be biased about this, but I do kind of think Google's approach seems a bit better. But it's a little riskier because on this slide here, you can see this yellow region. Google right now only has 1 logical qubit, but 1 qubit is something that we can simulate classically. In fact, we can simulate up to about 40 qubits classically. So anything that you can do on a quantum computer with 40 or fewer qubits, you definitely don't have any quantum advantage because a classical computer can just simulate your quantum computer. This yellow region is where once you've encoded your physical qubits into logical qubits, you're actually no better off. You still don't have a error-corrected logical quantum computer big enough to do anything interesting. So I mean, you can kind of see there's this big gap that Google has to cross if they want to take this fault-tolerant, error-corrected route to get to something that might be interesting. Whereas I think IBM's approach is maybe let's pick some algorithms where we don't need the error correction. We can have noisy qubits. It's not going to be able to factor, but maybe it can do something like quantum chemistry that would be more useful. So who knows what the future will hold.
Thank you.
Yeah, thank you for for the talk. It's really great, and it's good to know that we are safe. Yeah, so your conclusion and analysis is like based on Grover only. So, do you think there will be new algorithms, new quantum algorithms that will, like last year there were a Chinese team that they have a new Shor algorithm that requires less than 400 qubit. So nobody's sure about that. It's still not verified, but maybe we will have new algorithms that require less number of circuits, or maybe some hybridized between classical and quantum to break AES. What do you think about that?
Yeah, so the nice thing about my, I was careful to set up my talk at the beginning to refer to just these structureless known plain text attacks. And that's really nice because I can treat AES as a black box and rely on some theoretical results, which says that Grover's algorithm is the best you can do in the black box case. So unless you get some structure to your problem, you can't improve on Grover's algorithm. So then the question is, can we come up with a quantum algorithm that uses the structure in some way? It's a great question, and it might be the kind of thing that people won't come up with it until they actually start working with quantum computers. It's also a question that we can apply classically, right? So I'm not so worried about this for the same reason that I'm not that worried about a classical attack breaking AES. Just because it seems like it was, I'm kind of, I feel like it is possible to build things that look like black boxes for the purpose of cryptanalysis for both classical and quantum computers. So that's why I am focusing kind of just on the Grover attack and not something different.
Maybe a more general question, out of the crypto world, is there anything else we can do with quantum computing than just breaking crypto? Is this going anywhere else than just this?
Yeah, there are lots of things. So I mean, Grover search is a generic search algorithm, right? So as long as you have something that you can kind of, construct some sort of oracle function, you can get this speed up. What seems like one of the big applications that people are pursuing is quantum chemistry. And the rough idea here is that at the atomic scale, systems are quantum. And so it's actually very hard to fully model them classically because you have the exact superpositions that make quantum computers powerful. So the idea is, well, a quantum computer kind of represents that natively. And so that's sort of this green region here. And that's what the green line is here, is where on this chart we would start to see these kind of quantum chemistry algorithms. For me, I am a little bit optimistic about these, and maybe it's just because it's not my area, that maybe in the next couple of years, we would have a quantum computer that doesn't have error correction, but would be able to do something interesting and useful in chemistry. So that's kind of what I see as the big application.
Thank you. I also have one more question for you, Sam. You were very careful to just mention AES in this analysis, but what would be the case for instance, hash functions, SHA-3, or I don't know?
Yeah, so I mean, there's the question of the pre-image attack, which is going to look basically the same, because again, if you can't find any kind of structural weakness, you more or less are resorting to Grover's algorithm, and all the same issues apply. There is a whole field of collision searches, and so there's another theoretical result that says, arguably, it's kind of a normal collision search is a square root advantage, and it would be a cubed root advantage. The problem with this algorithm is it requires a lot of QRAM, and I'm kind of a big QRAM skeptic. I think it would take accessing quantum memory is going to have some cost proportional to the memory size, and so this will just kind of not work. And again, I have to reference Daniel Bernstein, who is, I think, published at CHES, maybe, making basically the same argument, that by the time you build the quantum hardware to get this 1/3 advantage, if you built the same amount of classical hardware, you actually get the same, you can run the attack in the same time. So I don't think, I'm sort of not a believer in the quantum collision attacks at all.
So another takeaway is that SHA functions can stay the same?
Yeah, that's my opinion.
Thank you.
Yeah, thanks again for the talk. I have a question. What do you think about applying Grover's algorithm to some of the lightweight crypto algorithms that only have 80-bit keys? Do you think that might be more feasible, or is that might also be impossible?
8-bit keys?
80-bit keys.
80-bit keys. Okay. I was like that. I have a simpler method. Yeah, so the thing about an 80-bit key is then you have but it's a good question. I'm not sure. There may be some kind of crossover that may be right around 80 bits where actually you don't need to parallelize so badly that you would get close to the square root speed up. And this really puts us in a funny range because what I've argued is that 128 is too big, where you need so much parallelism that you basically lost your square root speed up anyway. Let's say n equals 64, maybe n equals 70. You don't even need a quantum computer because the big classical adversary can break it. So yeah, right where in between, if any, is there a crossover point where you would get some sort of small advantage from your quantum computer? Yeah, it's really just kind of a, to me, sort of wild guessing at this point. I would generally feel like probably the classical computer will still outperform at these scales, just because the classical computers are really good.
Thank you.
But yeah.
Thank you for your talk. What do you think about quantum annealing problem and QO problem? And what are your predictions about this topic?
I'm a pretty big skeptic of quantum annealing. So, I mean, it doesn't have the same, Grover's algorithm, at least you have this theoretical guarantee that it should have the square root speed up. And as far as I know, there's no theoretical guarantees for quantum annealing. It's kind of, you're hoping that it catches something that should be at least as good as Grover's algorithm. And so I just kind of, I've never seen anything that convinced me that this is actually going to end up being performing at the level of a fault-tolerant quantum computer all the problems that it would need to. So I mostly just don't worry about it for cryptography. Yeah.
Thank you for your talk. I have a question. Is Grover algorithm useful for multi-key attacks on RAS? Would this be more realistic?
Yeah, there is a paper considering multi-key attacks. And it does get a bit faster. So maybe I'd kind of consider this as the same as my answer on an 80-bit key, right? That your multi-target is maybe reducing your effective attack complexity, and you still get some sort of quantum advantage, but there's maybe this very narrow region of this trade-off in what would be generally an extremely expensive attack, quantum or classical.
Thank you.
Thank you. We have time for one more question, maybe. If not, then let's thank the speaker again. We want to give you this token of appreciation. Thank you. And with this, we conclude our second plenary talk. And as I said before, Professor Prenell was here. We are deeply grateful for our two great invited speakers in this CHES 2024. So enjoy your coffee break.